Good afternoon, everyone. I am Divyanshi Patil, Associate Program Manager of C1973 EV Lab. Welcomes you all. As your host for today's webinar, on behalf of EV Lab and Varroc, I extend a warm welcome to all the participants joining us today. Today's session marks the second webinar in the series Evolution, titled Integrated Chargers or APM, Converters for Next-Gen EVs. Today's webinar is also enriched by collaboration between C1973 EV Powertrain Lab and Varroc. The lab was inaugurated on 8 Feb 2024 on the Golden Jubilee reunion of Class 73. The lab stands as a beacon of innovation in electric vehicles, established with a vision to accelerate the transition to sustainable transportation. The focus is on design, prototyping, and testing of key EV components like motor, inverters, controllers, and BMS. Additionally, we are privileged to have partnered with Varroc, a leading global Tier 1 automotive component company that initiated its operation in India's polymer sector in 1990. The company's specialization in the design, manufacture, and supply of exterior lighting systems, plastic and polymer components, electrical electronics components, metallic components supporting OEMs worldwide with a cutting-edge solution. Today, we have privilege to have our two distinguished experts. From Varroc, we have Mr. Mayank Dev, currently heads the Power Electronic team at the R&D Center of Varroc Engineering Limited. He has been associated with the automotive industry for more than 14 years, working on development of electronics for various vehicle subsystems such as ICE, powertrain, body control, EV powertrain, etc. Academically, he has completed a master degree in electrical engineering from University of Southern California, Los Angeles, USA. From IIT Bombay, we have Professor Chiladi Chakrabarti. He is an assistant professor in the Department of Electrical Engineering at IIT Bombay. He has completed his PE from Javadpur University in 2008, MTech from IIT Kanpur in 2012, and PhD from IIT Kharagpur in 2019. His research interests includes dual active bridge converters, PV inverters, wideband gap semiconductors, switch-based converters, integrated packaging of power switches, and high-frequency magnetics. Without further delay, let's dive into today's discussion. After a speaker's presentation, we'll have a dedicated Q&A session. Please use the chat box to submit your questions throughout the webinar. Now I would like to invite Professor Chiladri to share the insights.
Thank you, Divyanshi. So please let me know if you're able to see full screen.
Yes, sir.
Okay. So thank you everyone, wherever you are for attending this webinar on this topic of integration of onboard charger and auxiliary power module for electric vehicles. So the presentation will be in two halves. I will briefly sort of acknowledge the people who worked on this topic for this project, and then I'll hand it over to Mayank, who will start with a general discussion on to explain the theme of this kind of work and why it matters and what are some overarching challenges there. And then I will take over, and towards the latter part of the presentation, I will specifically talk about circuits-based integration approaches, and in basically try to compare and review various approaches and talk in detail about one particular approach. So myself and Mayank have already heard about. The other key members in this project who all work together was Shiva Prabhakar. He's my and Professor Sandeep Anand's PhD student here at IIT Bombay. And Nachiketa, who was also student here, PhD student here till some time, and he's recently joined Varroc, and Professor Sandeep, who was the PI for this project. We okay. So you are not able to see my second slide, is it? Okay, I'm changing the slides. Are you still on slide one? You still see slide one?
Yes, sir.
Okay, because I'm changing the slides from my side. Let me stop sharing and maybe just do full screen. You see it now? Yeah,
Yes, sir.
yeah. Okay. So, and other contributors from Varroc who also work with us were Dr. Prakash and Pramod, Dilip, Pawan, Vijayavardhan, Rohan, and Sai Pichapati. They all worked on this at some stage or the other, so we're all thankful to them. So with that, I'll hand it over to Mayank, who, as I explained, will start with a general overview of the topic and some of the challenges and basically making the case for integration and what are the challenges around it. So Mayank, over to you. So I'll stop sharing.
Thank you, Professor. Hey, please let me know if you can see my screen.
Yes, the screen is visible.
Okay, thank you, Devanshi. So I welcome you all in this webinar session today. And as Professor Shiladri mentioned, I'll be speaking on a general overview of what integration is all about and how it is typically done, what are the different avenues, what are the different philosophies of integration. And after that, I'll speak a little about what are the challenges of such a subsystem level integration presents in actual implementation. Before I go there, I would like to speak a little about Varroc. Uh, as Devanshi spoke during the introduction, Varroc started around the year 1990. And right now it is one of India's leading tier one automotive component supplier. And we supply different parts such as electrical and electronics, polymers, metallic parts to different OEMs, that is original equipment manufacturer or automotive manufacturers, not only in India, but across the globe. As far as geographical presence goes, we are present in 8 countries with 7,000 plus employees. And we have 39 operating manufacturing facilities, most of them being in India and few of them in Europe and Asia. Varroc has recorded more than 100 plus patents across different fields of innovations. And we have close to 7 R&D centers. I come from the electrical and electronics R&D, which is also working on developing EV powertrain subsystems for two-wheeler, three-wheelers, and four-wheelers EV market in India as well as across the globe. As far as the business side goes, Varroc has an annual revenue of approximately 910 billion US dollars. That is the last year's figure. And the business base is broadly located in India, and some part of it also comes from our global business. This is a small snapshot of who our customers are. As you can see, all the major global two-wheeler, three-wheeler, and four-wheeler brands are present as our customers, and we are proud to be catering to all of them. This is the brief list of contents or what I'm going to be speaking about, and we'll start with a generic overview of what EV powertrain looks like. What are the drivers and benefits of integrating different systems and subsystems of the EV powertrain? What is the logic behind integration and what are the potential avenues or possibilities of integration? And then I will be talking about a brief system level example of integration, which is same as the topic of this webinar, which is integration of OBC and APM. but I'll be doing it at a much broader level, at a system level. And lastly, I will be speaking about challenges faced in actual implementation when we try to integrate such subsystems. So the slide talks about the generic architecture of an EV powertrain to be specific. So it has been taken from the website of MG Motors. First, you have the high voltage battery, which is the equivalent of a fuel tank in a conventional vehicle, and it provides all the energy required for driving the vehicle. Then you have the electric heater, which is for maintaining the temperature of the energy storage system. Lithium-ion batteries, which typically go in EV, are not very good at performing at very low temperatures, so they need to be heated and maintained at a certain temperature. Similarly, you have at number 5 an electrical AC compressor, which does the job of cooling when the battery gets overheated. Then you have the electric drive transmission, which is nothing but connecting the motor to the drivetrain. You have a manual service disconnect. Manual service disconnect is an arrangement, safety arrangement, which is nothing but a mechanical switch, which disconnects the battery pack or splits the battery pack into halves and disconnects them from each other, so that when the vehicle is under service, there is no possibility of any electrical hazard to the technician who is working on the vehicle. Then you have the power distribution unit. It is nothing but a bunch of fuses and relays using which the vehicle controls the power distribution to its different subsystems. Then you have the high voltage wiring harness, you have the charging point, and you have a combined charging unit, which in this case is similar to an integrated onboard charger plus DC-DC converter. Now, this entire subsystem is fairly complex, so let's look at a simplified representation of the same EV powertrain and what is included in it. So we start with the charging port, where the AC supply comes from the grid, or a high voltage DC supply comes directly from a charging station, which goes to an onboard or portable charger. Portable charger typically in case of two-wheeler or three-wheeler EVs, where they may not carry a dedicated onboard charger. This charger basically charges the traction battery pack, which is controlled and regulated through a system called Battery Management System, or BMS. The main job of this traction battery pack is to supply power to two main subsystems. One is the drivetrain, which comprises of the traction motor controller, or in the language of power electronics, as we call it, inverter, and the electric motor itself. And it also supplies to something called as APM, or auxiliary power module, or low voltage, high voltage to low voltage DC-DC converter. Now, why this DC-DC converter is necessary on the vehicle is because, let's take the example of a very popular EV, Tata Nexon. Okay, Tata Nexon has conventional IC engine variants as well as EV variants, which are out there in the market. Now, if you look at it from Tata Motors' perspective, apart from changing the powertrain, it won't make sense for me to develop something which works at 400 volt just because I have a 400 volt battery present in the vehicle, because it will be costly. So what Tata Motors, or a company like Tata Motors, does is it develops the auxiliary subsystems and it commonizes them between IC engine variants and EV variants. Now, these auxiliary subsystems have been traditionally working on 12 volts or 24 volts in case of commercial vehicles, and their costs and their commercials have pretty much settled and has been standardized across the globe. So there is abundance of suppliers, there is abundance of component availability. So it is easy on the supply chain also. So what Tata Motors does is all the auxiliary components like speedometers, the infotainment system, headlamps, tail lamps, it commonizes at 12 volts. And in an EV, it will just take a high voltage to low voltage DC-DC converter, which will generate 12 volts from the 400 volt battery pack that the vehicle has. And the DC-DC converter will be used to supply all these auxiliary loads in parallel with an auxiliary battery. In addition to that, you also have a vehicle control unit. A vehicle control unit is typically used to execute the control strategy of the vehicle, which means the charging and discharging charging protocols, the battery discharge strategy, how much current the battery should be able to provide, different types of derating like electrical derating for the battery, thermal derating, all different sorts of diagnostics. Those kind of strategies are included in the vehicle control unit. And then there are auxiliary loads working on 12 volts like I talked about. Now let's come to our main discussion, that is integration. And what are the drivers or motivations behind the integration, and what are the typical benefits that one can achieve by doing such integration? But in order to do that, we need to first understand what is the value proposition of an EV. Okay, value proposition of any object is something, a set of qualities or features that can make that product or service very attractive to the customers who are going to buy it. The biggest driver for integration is basically improvement of this value proposition of an EV. As you typically know, you must have seen in the market, what are the two biggest value propositions that are driving the sales of EVs these days? First is the low running cost, uh, and the second is basically zero tailpipe emissions, which essentially make the electric vehicles greener than their conventional IC engine-based counterparts. But then there are also some other factors which are strongly working against this value proposition. We can call them knockout punches. So those two factors are the very high initial cost, mainly because of the cost of battery and the rare earth materials that typically go in the EV powertrain. And second most important cause is the range anxiety, because EVs basically need to be charged. Charging EVs right now takes time. And the third thing is that the range of an EV also depends on the driving style and environmental factors like temperature. So basically, in order to improve this value proposition, or in order to address these two problems of high initial cost and range anxiety, people have started coming up with different ideas of integration. Now, how integration solves these two problems is basically integration can support in reducing the weights of the component that go inside the vehicle. That means every gram of weight reduced gives you some improvement in the range of the vehicle. It also helps in reducing the size of the components, which means you can probably fit a bigger battery in the vehicle, or you can pack in more features which make the EV even more attractive. Faster charging by about two factors like weight reduction and size reductions. You can probably put a bigger size power electronics which can charge the battery faster, which can address the range anxiety. It can also to some extent improve battery life. Integration also eliminates some of the redundant components, which results into cost reduction. And all these things overall result into reduction of TCO, which is something called as total cost of ownership, which includes the cost for buying the vehicle, which includes cost of running the vehicle, maintaining the vehicle, and at the end of the life of the vehicle, scrapping the vehicle. All these factors together are called TCO, or total cost of ownership. Now, what is the philosophy and avenues of integration? When I say philosophy, what is the form that integration can potentially take? Integration typically can be done in three ways. One is co-packaging, which is nothing but putting two subsystems together in one enclosure. Just so that we are on the same page, when I refer to system, I'm referring to EV powertrain as a system, and different subparts of EV powertrain, I'm referring to them as EV powertrain subsystem. And when we talk about power electronic components or mechanical components, mechanical elements of these subsystems, I'll refer to them as components, just to make it clear to everybody. Now, co-packaging reduces size, and good example of that is something called as e-axle. It is nothing but integration of mechanical drivetrain parts like differentials with the motor and possibly the inverter. Similarly, you can also repurpose some of the subsystems or commonize some of the components. For example, same example, Tata Nexon, it has a feature of vehicle to appliance or vehicle to grid power supply, which means the vehicle battery can be used to generate 230 volts AC, which can drive some of the consumer equipments, or if possible, work as an inverter and can feed your home grid also. Uh, And then the third form is reusing or sharing the subsystem or components between two or more subsystems. And this is what we are going to talk about, or Professor Sheila Devi is going to talk about in detail. For example, integrating power electronic component between inverter and battery charger, or OBC and APM, or simply cooling system shared between battery pack and cable in electric bus. This is another example of where integration is possible. Now, if you look at the avenues or potential possibilities of integration, we can divide them at subsystem level, and we can also divide them at component level. If you look at subsystems, basically, for any two subsystems to get integrated, they must achieve some sort of synergy, and it is not possible to achieve synergies between all the subsystems of an EV powertrain. But typically, the subsystem which lend themselves very well to such an integration are listed here. For example, inverter and onboard charger is one such system. Inverter and auxiliary power module, or DC-DC. This is more popular in two-wheelers with lower voltage systems, where you can use a non-isolated converter with simply a buck converter or something like that, and just plonk it in the inverter box and they get integrated. OBC plus APM, or DC-DC converter, which is the focus of today's webinar, and battery pack and APM. This is again becoming popular in two-wheelers because the converter is typically non-isolated and small in size and power. Now, if you look at the potential possibilities of integration at component level, first is cooling circuit between different subsystems, power electronics devices, sensing and control elements like voltage and current sensors, microcontrollers which control the entire power electronics, gate drives, bridges, and stuff like that. Magnetics elements, transformers, and inductors, probably they can also be integrated. There's a lot of research going on that front as well. Bus bars and interconnects, which again add significant weight and cost to vehicle. Wiring harness also is a part of that. So now I'll talk about a practical example, which is the topic of this webinar also. Here the figure shows block diagrams of an onboard charger and high voltage to low voltage DC-DC converter. If you look at the block diagram of OBC, you have input coming from the grid, which goes through EMI filter to a PFC rectifier, where the voltage and currents are also sensed. And then you have the primary bridge with power electronics devices and the associated gate drive circuitry. It is fed to a high frequency transformer, and the high frequency transformer output is connected to secondary side bridge or low voltage side bridge and associated gate drive. And then you have output filter, secondary side sensing circuits, which are nothing but voltage and current sensing, temperature sensing, and the output of it is given to the high voltage battery for charging. In order to run this show, basically you have a control power supply, which controls all these internal circuitry, a microcontroller, and a communication module, which is typically in automotive is CAN, or controller area network. And all this is housed in an IP69 enclosure, which has either liquid cooling or forced air cooling. Similarly, if you look at the high voltage to low voltage DC-DC converter block diagram, the input is coming from HV battery here on the right side. Again, it goes through an EMI filter with primary side sensing, primary bridge with its own gate drive, high frequency transformer, secondary side gate drive, secondary side bridge, and the output filter with secondary side sensing. DC-DC converter also has its own control power supply, own microcontroller, own communication module, and a casing with cooling arrangement. Now, right at the onset, you can see there are redundancies in this. Some of the elements can be combined, some of the elements can be deleted altogether. How to do that, we'll see in the next slide. So if you can see what elements are redundant and what can be removed. First is we don't need to control power supplies. Typically in EV architecture, these control power supplies are derived from low voltage battery itself. So if we size the power supply such that it is adequately supplying power to both the subsystems, we can eliminate one of the control power supplies. We can also eliminate one of the microcontrollers. We can also eliminate one of the communication modules. And if you look at the HV battery side, we also get the benefit of having same wiring harness and same connector. Instead of having two wiring harnesses coming to charger and DC-DC and two separate connectors. So there also we are saving some cost. Now, if you look at this block, the output filter of the charger and the input EMI filter of the DC-DC converter input can also be combined to form bus link and filter unit. So there is also one element of integration possible. Some of the components can be eliminated there also. Now, another level of integration is possible on the primary bridge side. Can we integrate some of the power electronic devices? Can we delete some of the power electronics devices? Can we combine the gate drive? There is one possibility of integration. And then there is also a possibility of integrating the magnetics, typically in the form of multi-winding transformer, where there is some research has been going on. So if you look at all these things, they result into significant cost saving. In addition to that, your PCB becomes combined, your cooling circuit becomes combined, because typically when the charger is operating, DC-DC is supplying very limited power. So if you take a 3 kilowatt charger and 1 kilowatt DC-DC house together, when the charger is supplying to the HV battery, the DC-DC converter is not providing probably more than 200 watts of power, which is very less compared to the charger. So the cooling system needs to be designed for charger, and same will be adequate for the DC-DC converter when DC-DC is operating on its own and charger is not operating, right? So the combined block diagram of this integrated subsystem will look something like this. You will have only power supply, only one micro, one communication module, integrated output filter and bus link on the HV side, with only one module for HV side sensing of voltage and current, HV battery side bridge, which probably is some form of integration of power devices and gate drive, and probably an integrated set of magnetics. The EMI filter on AC side, the PFC rectifier, and that the grid side bridge will remain as it is. Similarly, the LV battery side bridge and the gate drive and output filter will also remain as it is. But together, this results into significant synergy and significant saving when it comes to overall system level performance. So all this looks really good at block diagram level, but it also comes with its own set of challenges. Typically, those challenges are in the form of topology and component selection, packaging and downsizing, EMI/EMC challenges, efficiency and thermal management front. There are some challenges, and the last front is the serviceability or reliability of the subsystems. Now, topology and component selection, when it comes to that, the application requirement of a charger in DC-DC are not like a regular power supply, because the high voltage battery as well as low voltage side of the vehicle, the load variation as well as voltage variation is significantly wide. In order to cater to that, basically the topology selection needs to be done very carefully. Wide bandgap devices, yes, we can use them. They also do help to some extent in this kind of a challenge, but they're not a solution for all our problems. Second set of challenges comes from the efficiency and thermal management perspective. You are packing so many thermally active components inside a single box. It is very difficult to cool them, and the cooling may also require some significant special efforts. At the same time, in order to keep the system cost low and the system size smaller, the efficiency requirements of automotive domain are typically very high, typically more than 95%, and not only at the rated power, but also at partial power as well as very low power. For example, a customer may demand you that the DC-DC converter should be more than 90% efficient at 10% of rated load. Right? And in case of thermals, somebody would say that, okay, I'll reduce the size and thermal management by going to higher frequency design. And that way I can reduce the cost as well as the size of the component. But that doesn't work almost thermally, because what happens is as you make the component smaller and sound smaller, their surface area available for cooling also goes down. Yet the efficiency doesn't improve significantly. In fact, as you increase the frequency, switching frequency, the losses may in fact increase. So this trade-off also needs to be balanced. Third set of challenges comes from EMI/EMC, where the EMI/EMC requirements in automotive are very stringent. And at the same time, you are operating two different switching subsystems, and at the same time, which can impact each other in terms of electromagnetic susceptibility. Then there are questions of different test applicability as far as regulatory standards go. For example, if you have an integrated OBC and DC-DC converter, the EMI standard for measuring something like emissions from something like a DC-DC is totally different compared to the EMI/EMC standard, which is used to measure the emissions from a charger, because it works from the mains grid, whereas DC-DC converter works on the DC side. And while solving EMIMC problems, if you do something to solve one problem, there is a high probability that it may affect some other area in your combined subsystem. So it may create another problem as well. So these things needs to be carefully traded off and balanced with each other. The fourth challenge comes from the space restrictions, which result into packaging and downsizing challenges. Downsizing you cannot arbitrarily do in these kind of applications because the electrical safety regulations and certifications like UL, which are mandatory in electric vehicles, have some certain clearance and creepage requirements, which make it impossible to reduce the size of the combined subsystem beyond a certain point. And the last challenge comes from the serviceability or reliability perspective. Basically, serviceability is a critical criteria for maintenance of the vehicles on the field, and OEMs strive really hard to keep the serviceability very easy so that the vehicles can be serviced quickly and very easily on the field. Now, this serviceability needs to be very carefully thought of during the system engineering of the integrated product that we are doing. Suppose you have integrated a DC-DC converter and a charger, and some element of the DC-DC converter fails. Okay. Now, what are you going to change on the vehicle? Are you going to change a particular component? Are you going to change a PCB, or are you going to change the entire subsystem, entire box? That needs to be thought of really in detail, because ultimately, if the product is in warranty, you are going to pay for it, or you will ask your supplier to pay for it if you are an OEM. And if the product is out of warranty, your customer is going to pay for it. And if you talk about replacing the entire integrated subsystem, the cost of that is obviously going to be more than an individual subsystem. So this is a major challenge that OEMs and tier ones need to think of in detail while implementing the integration. So that's all I had to talk about. Now I'll hand over the reins of the presentation to Professor Shiladri. Professor Shiladri, over to you. Thank you.
Thank you so much, Mayank. Are you able to see my screen? Is it full screen, right?
Yes.
Okay. Thank you. So I'll start with a brief repetition of some of the things that Mayank said, just to make sure that we all are on the same page. So this is like an schematic view of the power electronics and the electrical machines that you see in a EV. Shown here is a two-wheeler. So you have the onboard charger and the auxiliary power module and the three-phase inverter. Of course, you have things like BMS, but the onboard charger and the auxiliary power module is what we're focusing on in this presentation. And as Mayank said, range anxiety and charging time are two of the customer side concerns about adopting EV. So you can address them technically by going for higher battery capacity or going for higher rated chargers, and they're sort of linked together. So ultimately, that leads to, if you think about a future roadmap, you'll see this, all EVs are sort of ramping up maybe voltage levels to enable them to go to higher power levels of the charger, as well as of the motor and the inverter. So higher power rated OBC is something that's for sure is important and will come up more strongly in the future. Now, Mayank also talked about the case for having OBC and APM integration, right? And now on the APM side, if you look at vehicles, the demand for various automation features in vehicles are growing, which would mean that you would have more and more this low voltage auxiliary loads coming into the vehicle, and therefore it's not only the charging part, but also the APM's power rating is also expected to increase in the future. So given this, something which has to be higher power, you will of course encounter challenges with respect to power density, cost, and efficiency. So you have to try to improve power density, otherwise you can't accommodate that charger, right? So therefore, naturally, integration therefore seems to be a reasonable pathway to achieve that. And as is shown, basically what you're doing is you're having a multi-purpose converter which is doing functions of both the onboard charger and the auxiliary power module. So If we look at the structure or topological structure of any typical onboard charger, I showed only single phase ones. The most popular architecture is a two-stage architecture with a front end AC to DC converter, which is typically non-isolated, followed by an isolated DC to DC converter. So the oh, sorry, 1 second. Yeah. So the APM is by definition it's a DC to DC converter, which is connecting the high voltage battery to your low voltage battery. So therefore, the focus of this presentation is on this DC-DC converter stage topology, and what we can do to sort of integrate the OBC and the APM through having an integrated DC to DC converter. And if you look at popular topologies for isolated high frequency, isolated DC to DC converter topologies, you'll see dual active bridge, LLC resonant, and phase shifted full bridge as the most common topologies used in EV DC DC converters. Probably LLC resonant and phase shifted full bridge are more widely used, but these topologies have certain challenges associated with them. For example, in resonant converters, you essentially do power and power control by changing frequency. So if your battery voltage is varying over a very wide range, then your frequency might have to vary over a very wide range. Um, and there are other things which the resonant LLC topology cannot do. For example, if you want to do bidirectional power flow, then the simple diode bridge-based LLC, or even if you have an active bridge-based LLC in bidirectional mode, it works like a series resonant converter. So you probably have to go with more complex tank networks like CLLC and so forth. The phase shifted full bridge has issues of oscillations and those voltage spikes on the secondary side rectifiers because of leakage inductance in the transformer interacting with the output choke inductance. Uh, uh, so these are some well-known sort of challenges. I mean, but they're still probably the more popular converters used in industry. But as a part of this work, acknowledging these limitations, we decided to look at the dual active bridge, or as I will show in a few slides, a variant of the dual active bridge idea, using least number of active switches. But in general, you could go with any one of these sort of core topologies and try to play around with the concept that will show. So here's what, therefore, we are trying to do. We're basically trying to build a three-port DC-DC converter. It needs to have isolation between all the three ports. That's more or less steeply, mandated by almost all regulations. You need to have the provision to do simultaneous charging of both the main traction battery, high voltage battery, and the auxiliary low voltage battery, because when you're charging and auxiliary battery is connected to some critical loads, so you don't want to risk the charge of the auxiliary battery dying out. So simultaneous charging is something that is a good feature to have. And also you probably want to charge the LV and the HV batteries independently also, like if I want to just charge the HV battery, or I just want to do basically charging the LV battery from the HV battery only, which is the normal operation when there is no charger connected. So that's we'll refer to that as APM operation from now on. So that means that we are just charging the LV battery from the HV battery, and no charging port is connected. So the basic challenges in this are, of course, you're trying to charge two things at a time. So you could have voltage regulation and cross regulation problems, which I talk about. And then when you're making something integrated, there is a reliability concern because you're essentially repurposing some parts of the circuit. And so therefore, if something fails somewhere, it not only affects maybe the operation of the HV battery charging circuit, but also the other one. So just before I go on to a quick literature review of what the different approaches, just to show you that this kind of chargers are becoming common practice. There are industrial solutions out there, quite a lot of patents from industry. of this kind of chargers, because the value proposition, as Mayank explained, is quite evident for everyone to see. So now I'll sort of quickly give you an overview of the different ways in which you can do integration. So the basic first thing is, of course, doing package integration, which is, let's say you have an onboard charger circuit and you have an APM circuit, and earlier you used to have package them separately and connect them within the vehicle, but you can just now just keep all the electronics within a combined enclosure. And that's also integration, because as Mayank explained, that helps, still helps you in some sense, because you are saving materials with respect to the enclosure, with respect to the common heat sink and things like that. So that's really package or mechanical integration. That's a very basic thing that one can think of that will still yield some benefits. But we'll be focusing more on topological integration or electrical integration, which is what can you do at the circuit level also to enhance the benefits of integration. So if you look at that, broadly, you can classify them into two approaches. One is based using relays, and ones which do not use relays. And within relays based approaches also, you can have approaches which do not use any additional power electronics, and approaches which use additional power electronics. So the first one is this, which does not use any additional circuitry. So you have the basic charger. You have the basic charger circuit here, and you have a relay here. And if you want to do OBC operation, the relay connects to switch A, and then it's just like a normal OBC. And if you want to do APM operation, it goes to B, and then it does this connects to the battery. So basically, the way this functions is, of course, when it's connected to A, it's just like a normal onboard charger. So the front end acts like a PFC, AC to DC converter. When you're trying to do APM, remember, it's a DC-DC converter after all. So this front end converter here would be made to work like a DC-DC converter. Mostly it's a boost topology or totem pole PFC topology, which is essentially a boost derived topology. So in the reverse mode, it works like a buck converter, and you can make it work like that by just playing around with the control and the modulation. So you are essentially using the same power electronics, just using a relay to connect it from the grid port to the battery port. Now, there are some drawbacks of this approach. First is the fact that you are using a relay, of course. That's quite clear. A relay is a mechanical switch. It has some wear and tear. But looking at it from a circuits side also, if you think about it, normally if it's a PFC, then this might be, let's say, 230 volts, and this voltage on the DC link is something like 400 volts typically. And if you have to leverage this same front-end converter to charge a relatively low voltage battery, then this converter has to work from 400 to, let's say, 12 volt or 24 volts. So that's a very high step down ratio. And that would mean that this converter is essentially going to be very, very inefficient in itself. It would mean that the voltage rating of the switches here would be, of course, be decided by the DC bus voltage, which is relatively high, 400 volts or so, but the current rating would be decided by the very high currents on the low voltage port, which would mean that you are essentially, it's not a good design. Same thing saying that the converter is inefficient when it works with very high voltage ratio. So while this avoids any added power electronics, is a simple solution in some way, it still has those two key disadvantages. It uses a relay, and it's not likely to be very efficient. There's another disadvantage that it has. I will talk about it. But using relays, you can also add some power electronics and get rid of the disadvantages of the last approach. So here is one way to do that, in which you have an added circuitry here. Okay, so when you're doing onboard charging operation, this is just off, and this just works like a normal charger. And when you want to make it work like an APM, now you connect this high frequency transformer here. Okay, and then there's another high frequency AC to DC converter. It's really a bridge architecture. And you operate this, remember, as I said, this could be a front-end converter or something like that. Typically, that is also a full bridge. So you can operate this full bridge also in high frequency mode to generate a high frequency waveform here, which does not have a DC component, and then you just use this transformer and this full bridge to transfer power to the HLV battery. Now, because you have introduced this transformer here, you can play around with its turns ratio, and that helps you to address the previous challenge, which was that even if the voltage here and here they are quite different, this transformer here can take care of that. There's another similar approach which I'll talk later, which essentially also uses added power electronics, but as I will show later, that this one uses one bridge less. Okay, so this integration, which is being done in some sense by using this relay, is actually adds power electronics, but let's say it adds 75% of added power electronics compared to what I will show in a few slides from now. But it still uses relays. Okay, so that's a bit of a concern, of course, and you have this kind of connection. So there's leakage inductances here. So your transformer has to still work well considering those things. So those are some practical challenges that you should be aware of. Right, and the other thing which is common with any sort of relay-based approach is is that you cannot do simultaneous operation of onboard charging because it's just multiplexing and it's hardware multiplexing, right? So you can't do either you're in OBC mode or APM mode. So that's a big disadvantage in applications which I talked about. If you want to be absolutely sure that your LV battery is always on, you would want to have a simultaneous charging feature, right? And of course, because there's additional relay, it's reliability challenges, cost and volume challenges. And I've talked about the other thing, that the power flows in multiple stages here, so you could have a poor efficiency because of that here. And here, by virtue of the fact that there are no added power electronics, but this is a really high voltage step down, the efficiency there is also a concern. Okay, the next approach is you just integrate on the DC link, which is you put another DC-DC converter. You have a two-stage topology, so you can just have an isolated DC-DC converter. Remember, you need isolation between all the ports, so this converter needs to be isolated as well. And that also can work. So this is sort of very similar to the simple case of package integration, where you essentially have a DC-DC converter, connected between your HV battery and your LV battery. Okay. So this is kind of very similar, but this there are situations when you would want to prefer this versus this, and the as you can see here, for example, when you are trying to do simultaneous charging, the power comes here on the DC link, and some of it goes to the LV battery and some of it goes to the HV battery. Whereas if you're trying to do simultaneous charging with this mechanical or package integration, the power that will come from here needs to arrive at the HV port. Then some of it charges the HV battery, and then the further part which needs to charge the LV battery needs to go further downstream. So in short, if the power that reaches the LV battery has to go through many stages, one stage more in this case, and therefore if your mission profile is such that you have more or less close enough power distribution between the two load ports, let's say in general, then probably this is the topology that makes more sense. Okay. There's another case when this topology would make sense. Let's say you have a very high voltage battery, 800 volt or so, and your intermediate DC bus voltage is somewhere in between. So then it would also make sense to probably go with this topology, because let's say this is 800 and this is 600, and this is, as I said, 24. Then you would rather do a 600 to 24 than an 800 to 24. So based on the use cases, the mission profile of your load, and the voltage levels, you can select either of the two. Now, if you think about this versus the relay-based with power electronic solutions that I talked about, so remember I said that uses a little bit of less power electronics, because within this DC-DC converter, typically this is isolated. So you would have an input bridge, you would have a transformer, you would have an output bridge. So that input bridge is what is missing in the added relay-based approach. So that saves you that much, in terms of efficiency, size, cost, and things like that in the relay-based approach. Though this, remember, now you can do simultaneous charging. So that's the trade-off. You get this feature, but you probably will be a little less efficient. Okay, the final broad approach for integrating, and this is probably the most common approach in literature, is integrating on the high frequency side, and that can be done using multi-winding transformers or using two winding transformers. So multi-winding transformers is a simple idea. You have a three winding transformer, and you have, this is the front end converter, and you have a bridge here, a bridge here, and a bridge here, full three full bridges, let's say, and they're all coupled using a three winding transformer. The equivalent circuit looks something like this. You have this high frequency AC sources, and you change the phase shift between each one of them, and you can control power flow, okay, between any one of the three ports. But the problem, there are a few problems with these approaches, which can be addressed through clever design of the transformer and modulation and control for sure, but nonetheless there are challenges to be addressed. The first of this is um, mm, the control among the three ports is coupled. For example, if you change the phase shift between V1 and V3, it not only changes, keeping, let's say, the phase shift of V2 same with respect to V1, it changes the port power not only going into this third port, but also in the second port, which is what you would not want. So the cross regulation between the two ports is very difficult to achieve. And let's say you have another example where you want to do not simultaneous decoupled power flow, but you want to just send power to the HV battery, let's say, and you don't want to send any power to the LV battery. Okay, now you can't achieve that in this sort of topology easily, because if you just even take off the gate pulses here, then because of the diode's conduction, some power will try to flow to the capacitor DC bus, which is why in this kind of, this is an example of how you can avoid that, is you can sort of hardware isolate the low voltage DC link from this side by just using a four quadrants device. Okay, so that's the added complexity that comes into the picture, because with this kind of three winding transformer approach, because the current always has a path to flow even when you withdraw the gate pulses. And if you try to actively try to make the power zero by giving gate pulses and making the phase shifts zero, that also doesn't quite solve the problem, because even though the active power flow would be going to the port would be zero, it would have circulating currents in the windings, and that would increase. It would mean that even though you're not sending power, you have losses. So those are the challenges which exist in this approach. And interestingly, some authors have also reported that when you use a three winding approach, then the volume of the combined three winding transformer core can be, in fact, more. It can be higher than when you're using a non-integrated circuit with two different transformers. This would probably differ from one design to another, but it's certainly not generally true that an integrated approach gives you a smaller transformer size compared to non-integrated design. Finally, we come to the final approach, of electrical integration, which is sort of a switch leg-based approach. So if you think of this is the motivation which is reported in this work, which you have sort of two separate converters, and both of them are, let's say, using a bridge. So why can you try to combine the two switch legs? And you can do that, and you end up with this kind of a topology. Essentially, these two legs are same, and therefore they must be connected to a common transformer winding, which is what is done here. So you have two transformers and they're connected, and this is that common switch leg. Okay, the few advantages of this approach are that you are using, there's no magnetic coupling across the three power flow paths. Okay, as because there's one voltage here and another voltage here. I will explain this in detail later on, but there's no direct coupling between the three ports. And the just if you compare this approach, the integrated approach with the non-integrated approach, grossly speaking, there's efficiency improvement. So you are not only saving in terms of switch count and losses and switch count, size and cost, but potentially improving the efficiency as well. So now I'll talk in the next 5 minutes or so about a specific targeted application that we looked at. So it was about charging a high voltage battery and low voltage battery, where along with this basic requirements of isolation and simultaneous power flow and independent charging, we were looking at in an application where we were okay with unidirectional power flow from the utility grid to the HV battery. and from the HV battery to the LV battery. Okay, so this is the use case for a large number of cases in industry and commercial products right now. It really, I mean, people talk about V2G as and things like V2X as future features which are coming up, but immediately these are things that you will not find in most chargers even for four-wheelers. So given that, and given that, let's say you're catering to the light electric vehicle segment, which where cost is important, you would want to bring down cost not only through reduction, but what further enhancements can you do to leverage the benefits of integration. So so you can think of a modified low active device count based converter, and here you get rid of some of those active switch legs very judiciously, and you introduce half bridge capacitor legs or diode bridge legs, and you are left with a topology which uses the least number of active devices needed for the specified power flow directions. And that is, you have a one source port, okay, one port which is a source as well as a load port. So with respect to the input side, it takes power, so it's a sort of a load port, but it needs to, when in APM mode, this is feeding power back, so it's also source port. So this is a bidirectional port, and the LV battery you are sort of using to always sync in power. So you have one source, one load, and one source and load port. So if those are given as use case specifications to you, then you can sort of come up with this topology. Uh, uh, and another thing I should have mentioned is the voltage just specified on these ports also are an important design consideration. If you have a voltage which is much lower than this, then to reduce the transformer turns ratio, then just smartly choosing the where to put half bridge capacitor legs. For example, if you put a half bridge capacitor, it reduces, gives you a step down turns ratio of half. And similarly, use a half bridge capacitor over here, because let's say this is 400 volts or so, and maybe this is 120 volts. So if you use a half bridge here, it's straight away makes your transformer design relatively easier, because the transformer is seeing lower dVdt. You are you also require lower turns ratio. So you have several advantages there: lower winding losses, because lower capacitive coupling effects, because the number of turns are also going down. And but yeah, in principle, if you have to transfer power to the LV battery, you could do this with just a diode bridge rectifier fully, because this is not, that does not need to source. But given this idea that you would want decoupled power flow between the three ports, you would want to make one of these legs, just one is enough, active switch based, and that combination now. So if each bridge, if you see there's only one active switch leg, that gives you all the features that we talked about with gives, you have operating with the lowest number of switches and gate drivers, you have decoupled power flow, and you have the least transformer turns ratio that you can work with. So a quick explanation of how this sort of circuit works with some operating waveforms to explain. So basically, if you look at the primary bridge here, S1 and S2 operated with simple 50% duty ratio, it creates a high frequency voltage VAB square wave. Okay, on this side you have S5 and S6, which is your sort of your control leg here. You operate that those also with sort of square waves operation, and with the diode leg, current flows and the current decides when the diode is turn on. So you end up with a quasi square wave waveform on this side, VCD. And now if you look at VAB and VCD, and there's this leakage inductor, it's very much like a dual active bridge. It's actually a semi dual active bridge topology, and the phase shift between your primary side switch S1 and your, let's say, secondary side switch S5 is your control variable, a control variable which decides power, how much power is flowing through the stop transformer, and ultimately how much power is drawn from the input side. Similarly, if you look at now what is happening on this, through this transformer S5 and S6, you are switching, it also creates a square wave between this node and the capacitive half bridge node. And you have sorry, this should have been S7 and S8. This is the control switch leg on the tertiary bridge, on the LV side bridge. You also operate them with 50% duty ratio. Again, with the semi-dual active bridge principle, it generates a quasi square wave voltage waveform. You have phase shift between S5 and S7, and with that, so that is a phase shift control variable. You can control power that is going through this transformer and to this output port. So this sort of operating principle is summarized. The actual expressions of power flow and current are quite complex, but if you look at functionally, your input current or the power that is flowing through this transformer is a function of d phi 1, and the power that goes to this output port is a function of d phi 2. So if you just change d phi 2, only this power changes, and if you just change d phi 1, this power changes. They do not affect each other. So with that, you can think of a complete block diagram of the control loop. So you would have a direct feedback of this LV side current, and compare with the reference coming from the BMS that goes to a controller, which sets the phase shift value to be decided, and which ultimately goes to the modulator, and your current comes out of it. For this, there's one added consideration, because remember, d phi 1 controls the total power through this transformer, the input current. So that current needs to be decided from an outer loop, which is because ultimately we want to control the power, charging power into the batteries. So you have this reference current here, and the current from the is feedback from the sense from this part of the circuit, and you pass it through a PI controller, which automatically decides how much power should be drawn from there. So it's a sort of a cascaded current loop structure similar to the PFC front end. But fundamentally, you have these two control variables, which is allowing you to do this kind of operation. If we did some basic loss sort of comparison of this kind of integrated approach versus a non-integrated approach using similar sort of device counts, okay, same device count, and not same, I mean the same approach, but with the half bridge things remaining same, and the same sort of dual transformer approach. So we see that we get a 5% improvement, 0.5% improvement in efficiency for the devices that we use. And this is similar to the result that I talked about a little earlier in the presentation with the full bridge bidirectional topology that these people had reported. So not only are you sort of getting rid of this additional switch leg and the gate drivers cost, you are also potentially improving the efficiency without foregoing any of the control sort of benefits here. Here, I should say that one of the big advantages is everything is nicely decoupled. But so also here, if we are controlling it properly. We sort of verified this thing experimentally, of course. There are some images of our experimental hardware and the lab setups. So just to show some experimental results, when the charger is only working, you take power from the grid and just charge the high voltage battery. So that's OBC alone mode. These are operating waveforms. The primary side is a square wave. The secondary side, VCD, is a quasi-square wave, as I said. And this is the current through the high frequency transformer, the output current. And similarly, if you look at when the only the APM works, which is power comes from the HV to the LV port. Again, VDE, the input side or the sending side is a square wave. The receiving side is a quasi-square wave. You have the leakage inductor 2 waveform here and the output current. And you could also have power flow simultaneously done, where now you can see there you have all the two quasi square waves and two square waves, as well as the two high frequency waveforms, all shown in one common trace. So this is very similar to the first slide that I earlier slides that I showed, where I had all the key waveforms all together in one place. So just to conclude, a final couple of slides. So this approach that I talked about is actually, if you think about it, it's ultimately a multi-port DC-DC converter. So any sort of DC-DC application which is multi-port, 3-port, you can think of using such approaches. And especially if it is essentially the same sort of mission profile specification. For example, again, one source port which not need to sync power, for example, if it's PV, and then you have another port where you have battery or energy storage element which needs to source as well as sync, and maybe you have just passive load where you are just sending power all the time. Then this kind of topology also makes sense. And maybe in a small scale PV application, the power levels would be and the voltage levels would be very similar to what we have considered in this case. So to finally to look at some key things for you to take away from this presentation, there's a growing demand for higher power rated onboard chargers and APMs to mitigate the EV adoption related concerns, and integration of these two elements could provide a significant efficiency weight advantages, and thereby offering cost reduction benefits. Now, if you just do mechanical integration, also that also can give you some benefits because of lesser material use for heat sink, enclosure, etc. But electrical integration enhances those benefits even further. And there are different, broadly speaking, four different ways of doing electrical integration: relay-based, DC-link based, three-winding transformer-based, and a common switch leg-based. Each one has some challenges, some good points and bad points, which I talked about. We and the three-winding transformer in particular has some control coupling challenges, which can be addressed through things like decoupling matrix and designing your transformer properly. But these are challenges which exist there. So we have looked at a modified load device count integrated power converter topology, which is very specifically sort of optimally suited for the load flow directions, the power flow directions. Operates with the least active switch count. It has low transformer turns ratio because of the use of the half bridge legs, and through control you are also able to ensure decoupled power flow through the structure as well as the control. We have validated it experimentally, and but there are still scope for improvement in this sort of area. If you're interested in working, for example, the design, the optimization of the design and the modulation is still something that can be worked on, because as Mayank mentioned, in practice the batteries operate over a very wide voltage range, and so you probably want to build a product that can cater to that kind of wide voltage range, maybe not from only one supplier but from multiple suppliers. So that really makes the problem even more interesting, and you need to look at the integration from a different perspective. And the reliability aspect of integrated converter structures is also something that is an interesting topic. For example, if you are integrating something, as I mentioned, if you have this common switch leg, then if that fails, then you would potentially, both the high voltage charging path and the low voltage charging path are disabled, right? Which will not exist in a non-integrated or a modular structure. So that's one of the advantage of going modular or non-integrated, is you have more reliability. But it's also interesting to note, if you remember, I showed that the non-integrated structure has poorer efficiency than the integrated structure. Part of that is it has higher losses, and reliability is ultimately decided on temperature and losses. So that's something of an interesting study of whether the improved efficiency and the lower losses actually does not compromise reliability so much. Uh, so yeah, these are some of the things that we want to discuss, and both of us would be happy to take any questions from the audience.
Thank you, Professor Shiladi. We have a question in our chat box.
Yeah,
The
can you read
question
it out?
is,
Yeah.
yes. The question is there any voltage balancing issue you have observed in modified low active device count IPC?
Sorry, can you
Is
say?
there any voltage balancing issue you have observed in modified low active device count IPC?
E- uh, Voltage, I mean, if the person who has asked the question, maybe he can unmute and speak up, that would be good. But in terms of a voltage balancing, I'm not sure if you're referring to which elements you're referring to in terms of voltage balancing among which elements. uh, if you could just unmute yourself, or just add some
Voltage
more detail.
voltage balancing
No, no,
issue, the
I
output.
can see the question, Divanshi. I just
Okay.
yeah. Okay, so I can maybe you can unmute, or maybe I can move on to the next question, which is using diode instead of MOSFET may increase the conduction loss and reverse recovery loss. Whether using diode will give any. Okay, so if your topology is designed to ensure source switching, then reverse recovery is not such a big problem with diodes. If it's Hertz switches, then it's of course a big issue. And conduction losses is also an interesting thing, because if you use good Schottky diodes, which are very well rated, typically if you are using a MOSFET, and if you're comparing it with its own body diode, then of course it makes sense to use the MOSFET. But if you're just trying to compare a controlled MOSFET device with a very well chosen Schottky diode at a given current level, then the conduction losses might not be too different, um, actually. Uh, diodes, the ones which we're using, if you've seen, we're using it on one of the LV side ports where the currents are not too high. And as I mentioned, if you're using Schottky diodes, probably it's not such a big issue. But of course, if you want to improve efficiency that way, you can select very good devices, I guess. Uh, but the point here is that you use diodes not only to sort of, you use active switches where you absolutely need to. So that's the point. You're not using active switches, or you're not using diodes just for the sake of it, but you are using the minimal number of active switches that you need. Uh, I mean, we could have just used, as I explained, a diode bridge on totally on the LV side, but that would have reduced controllability and decoupled operations. That's why we put in that extra switch leg. Uh, Voltage balancing issue in output bridge capacitor. We did not. I think we did not face any such issues. The power level of the converter, it's something close to several kilowatt, couple of kilowatt on the main side, and the on the low power side is sub kilowatt. It's at that level. Okay. Different layers of isolation required in the control and power supply side. So I think, Mayank, in general, everywhere you have, if your question is required, whether you are asking this from a standards requirement or an industry requirement, I don't know, but I'll just quickly, briefly state what uh, exists. If you see this topology, then there's isolation between all the power ports, and of course, uh, isolation between the grid and the high voltage battery is and also the low voltage batteries is a clear requirement in almost all EV products. Mayank, if you might want to
Yeah, so
share
there
your.
are a couple of standards. One is called ECR 136, that is the European standard, and the Indian equivalent of it is AIS 156.
Right.
These standards clearly mention the isolation requirement. Typically, you require double isolation or reinforced isolation for both the main power converters as well as control power supplies.
Right. Yeah. So so the next question was sort of similar. Is isolation required for onboard charger? I think I would say this is sort of a, based on standards, you would say yes. And if you go for, I don't remember seeing any commercial product out there. There are papers that I've seen, where academic papers where people have written about having non-isolated onboard chargers, but I think there's some disconnect between what the standards are asking for. And in terms of ground currents, if you have non-isolated converters, ground currents are always a problem. So ultimately, I think it's a ground current related stipulation also, that your ground currents under some fault condition cannot exceed something. So isolation automatically helps you with that.
Yeah, isolation and electrical insulation, basically insulation resistance requirement, those are given in the standards, and these are regulatory standards. So without meeting those, you cannot sell anything in the market.
Right. Next question is, integrated converters capable of driving traction motor? Yeah. So as Mayank said in his early slides, that is also integration can be done at several aspects. That's also a big area of research where people are talking about integrating the traction inverter and the charger. But similar kind of debates come up over there also, because some people then start using the motor winding inductance and the charger becomes non-integrated. But for this work and for this webinar, we of course focused on OBC plus APM, but certainly that's a research area that people are looking at. Specific level of isolation, I think Mayank already answered that. Isolation mandatory, again, it was answered. Is bidirectional APM more important in eliminating pre-charging circuits? I'm not sure which part of bidirectional, because the APM operation is certainly unidirectional. So, Abhyadeep, if you can follow up on that in text, it would be helpful. Uh, which sensor is used for phase current sensing, shunt or Hall effect or integrated? Yeah, I think we used a Hall effect sensor here. Yeah, so only question I think, okay, what is the light load efficiency of this proposed converter? Any numbers that you have in mind? It's so Shiva, who's my student, who's with me, tells me that it's greater than 90%. So actually, that is something that we have worked on. We didn't present today. It requires careful design and optimization to do that. If you operate it in a certain way, then the light load efficiency probably will not be that great. But there are ways to address that through design and modulation, and we were able to achieve greater than 90% over light load. Okay, when you combine charging of high voltage battery with BMS, with no BMS, how do you control the charging strategy? Okay, I think we did not focus on BMS for this work, but high voltage battery with BMS and LV with no BMS. Mm, I think that is really not what the scope of this work. I mean, BMS is also something that actually people have, maybe I can think of some work which was done where people have integrated the BMS and the charger power electronics also. Uh, so coming back to the other question on integration, so you can integrate charger and inverter, you can integrate charger and APM, and you can also, there have been people who work on integrating charger and BMS. But we have not looked into those aspects of how we
Professor
control this.
Shiladri, if I may interject, sorry.
Yeah.
See, it all depends on where your control strategy for charging the high voltage battery resides. Because as far as low voltage battery is concerned, it's really robust. So if you look at a typical conventional four-wheeler or two-wheeler, there is no control on the charging of vehicle. There, the converters operate in constant voltage output mode. Either the vehicle alternator and a rectifier, or the magneto and the regulator rectifier in two-wheelers. They operate in constant voltage mode because lead acid battery is robust enough to take that kind of abuse and still survive for a long period of time. So the charging strategy is actually implemented only for the high voltage battery, unless for low voltage in some application people are using lithium ion, but I don't see that use case very popular. People typically stick to lead acid batteries. So the charging strategy is typically either contained in the VCU or in the BMS, depending on how functional partitioning has been done on the vehicle side.
Right, right. Thank you, Mayank. What about thermal analysis? Well, we did. We must say this was just a demonstrator. We didn't look into the mechanical aspects in detail, but yeah, thermally, uh, uh, and under lab conditions, at least with the kind of efficiencies and the numbers, the power numbers were, as I mentioned, just a couple of kilowatts or so. So it's not very high power. So we did not face any significant thermal challenges in the lab scale environment, at least. Switching frequency was about 100. What was the switching frequency? 100 kilohertz. Can we keep different frequencies or the size of the APM increase with integration? Uh, can we keep different frequencies? I'm not sure, understand if you mean to say that whether the frequencies of the different parts of the bridges can be different, then no, because there's a common switching leg in the non-integrated circuits. You can do that. To avoid, okay, so Abhyadeep has a follow-up to his earlier question, yeah, which is, does the APM help in eliminating pre-charge circuits? I have to think about that. So by pre-charge circuit, what he means is to avoid the inrush current which flows when going to the HV battery. So Mayank, you have any ideas on that? And the sort of the APM sort of, can it sort of help in?
It can be done. Basically, I'm not sure from the topological perspective whether it is possible or not, but in some cases where the DC-DC converter is there, it is possible, since the wake up happens on low voltage side, it is possible to recharge the high voltage side battery by operating the DC-DC converter in the other direction, so that when the high voltage side contactor closes, there is no inertia. But typically, I've seen that people prefer to use recharge contactors with integrated recharge resistors and all that, because they are kind of more robust.
No, I mean the other thing that comes to my mind is yeah, the if you look at the DC-DC architecture of the active bridge structure, unlike a PFC, which has so there's a pre-charge there's a inrush current problem on the intermediate DC link capacitor bus, right? And there's a way to deal with that. But by operating the active bridge circuit modulation also properly, there's a way to slow charge your output capacitor of your isolated converters also. So that is also something that can be done. I mean, um, not necessarily feeding power back from the LV battery, but feeding power from the high voltage bus and slowly feeding it back, feeding it to the output side by controlling the modulation switching signals of the main traction inverter side. The next question is, how do you integrate CAN with LV charging? Mayank, any view on this? I think it's
So typically in these cases, the CAN is on LV ground itself. Because the VCU is typically on LV ground, which is kind of the master controller or the brain which controls all the charging strategies, deratings, diagnostics, and all that. So it is not very difficult to integrate CAN on the LV charging side. It's on the same ground, so it's just adding one communication module on that ground actually.
Okay. Okay. I don't see any further questions. Are there any further questions, Divanshi?
No, sir.
Okay.
If there will be any questions, we can reply with the mails.
Sure. Okay. Thank you then, everyone. You want to say a few concluding lines, maybe, to thank the audience?
My sincere thanks for your exceptional presentation to Professor Shilagri and to Mr. Mayak and to all the participants who have given us time.
Okay.
So further, we have few more questions, so we can revert them through mails.
Yeah. Thank you. Thank you,
Thank you
Divyanshi.
again for
Thank you for the
sharing your
opportunity. Thank
knowledge.
you, Mayank. Yeah. Thank you very much for inviting, and thank you, Mayank, also for making working with me to make this presentation.
Thank you, Professor. Thank you, Shilia. Thank you, Divyanshi. Thanks for giving me the opportunity to share my knowledge here. Thank you very much.
Thank you.
Thank you.